Here's a question which involves looking at the acceleration of a rocket, which is subjected to a thrust force as well as to the Earth's gravitational field at a certain height above the ground. Now, if you'd like to see anything similar to this in the future, or if you have any suggestions for new topics or specific problems that you'd like to see on the channel, let me know in the comments. So let's read the question and let's try to understand what it wants. So we're dealing with a rocket, obviously, and it says here that the gravitational acceleration is 8.69 meters per second squared. So it's clearly at a certain height above the ground, which is actually given to us as 400 kilometers. And we know the mass of the rocket is 300 kilograms. So that's m equals 300 kilograms. And the rocket is heading 30 degrees with respect to the vertical line. In addition to that, we're given the thrust, and the thrust is given as 4 kilonewtons, so I'm going to convert that into newtons. And then the nozzle of the rocket is tilted at a 1 degree angle with respect to the heading of the rocket. Okay. And what we're asked to find are actually three things. We have to find the x and y components of the acceleration of the center of mass. And then we're also asked to find the angular acceleration alpha, right? So we have to find the angular acceleration and then the x and y components of the acceleration of the center of mass. And we're also given the fact that the radius of gyration is 1.5 meters. Okay, so let's see how we would deal with this. Now I'm going to redraw badly this rocket. I'm just going to draw it as a rectangle. And I will draw all the forces acting on the rocket. So the first thing we have is obviously the weight, which is acting downwards through the center of mass, and that's going to be my mg. And other than that, we just have one more force, and we're ignoring any air resistance at this point. So the other force that's acting is, of course, the thrust. So this is the direction of the rocket's heading, which is at a 30-degree angle with respect to the vertical. And then the thrust force is acting something like that. Again, it's a bit exaggerated, but that's to be clear that it's not along the heading of the rocket. And then if you use a bit of geometry, you should notice that this angle here is actually 31 degrees. And when we do the calculations, it's not going to make too big of a difference compared to if it was 30 degrees, but that's the correct value of the angle. It's 31 degrees. So it's this 30 degrees here, and then it's tilted 1 degree more, so we add those two together. Okay, so let's see what we can write in terms of the forces and how we can apply Newton's second law for this. So first of all, we're going to look at what happens in the x direction. Now, normally we have to choose what's the x and what's the y direction, but this problem gives it to us as being to the left, right? So my origin of the coordinate system is going to be in the center of mass, and then my x direction is going to be to the left, and my y direction is going to be upwards like this. Okay, so let's see what forces are acting, or what forces have components acting in the x direction. So weight doesn't have anything going on in the x direction because it's purely vertical. So the only thing remaining is the thrust force. The thrust force has a component in the y direction, which is this one here, right? And this is the thrust times cosine of 31 degrees. And in the x direction, we have this right here. So this would be t sine of 31 degrees. Okay, so in the x direction, we have thrust times sine of 31 degrees equals mass, let's use capital M, times ax. Okay, and this is one equation, one unknown, and we just have to find what ax is. So let's try to do that on the next page. So AX is going to be T sine of 31 over M. So T is 4,000 newtons. So 4,000 times, and then sine of 31 degrees is about, well, it's close to 0.5 because that's what sine of 30 degrees is. But to be more precise, this is about 0.515 over the mass, which is 300 kg. So the value that we get from here is going to be about 6.86 meters per second squared. Okay, so you can approximate that to 6.87 if you wish, but I'll just leave it like this. Right, so let's look at how to find the acceleration in the y direction. So in the y direction, we have two forces, right? We have the weight and we have this here as well. So let's write that like that. So in the y direction, we have one force which is acting in the positive y direction, which is t cos 31. So that's t cosine of 31, and then minus mg, and that's m times ay. Okay, so ay can be found by dividing everything by the mass. So that's t cosine of 31 over m minus g. Okay, now keep in mind g is not actually 9.81 because we're 400 kilometers above Earth, so we have to use that 8.69 instead. So what we have is 4,000 for the thrust, and then cosine of 31 degrees should be about 0.857 over 300, and then we subtract the 8.69. Right, so let's see what we get. So the first fraction is going to be about 11.426 minus 8.69, and that is approximately 2.73 meters per second squared. Okay, so those are the acceleration components of the center of mass in the x and in the y direction. And there's one more thing left to find, which is the angular acceleration of the rocket. Okay, and in order to find that, we have to apply Newton's second law, but for rotation. Okay, so let's see how we do that. Now, what I'll write here is that the sum of moments about the center of mass, where counterclockwise is my positive direction, equals the moment of inertia about the center of mass multiplied by the angular acceleration that we have to find. Okay, so here's how we can do this. I'm going to draw my badly drawn rocket again, and then we know that the thrust vector is inclined at a 1 degree angle with respect to the heading of the rocket. So what we can actually do is we can split this up into a component of thrust which is acting along the heading of the rocket, which is this one here, right? And this one is t cosine of 1 degree, and then the other one is t sine of 1 degree. Okay, so we have the center of mass somewhere here, and we know the distance from the center of mass to the nozzle is 3 meters, and then we can use this formula here. So let's see what we have. First of all, above the center of mass, the weight doesn't actually produce any moment. So the only thing we have left is the thrust force, but from the thrust force, it's only this component that produces any moment, because this component is acting along the rocket's heading, so it doesn't actually produce any thrust. Therefore, what we have is the following. We have minus t sine of 1 degree multiplied by 3. Now, the reason I put a minus is because this moment is actually clockwise, hence it's negative. And this is equal to the moment of inertia of the rocket, which is the mass of the rocket, that is 300 kilograms, times the radius of gyration squared, and that's 1.5 squared, which is 2.25 times alpha. So the only thing left to do now is just to find alpha, and alpha is going to be minus, and then the thrust is 4,000, and then sine of 1 degree is going to be something very small. It's going to be 0.017 times 3 divided by 300 times 2.25, which is 675. And finally, we have a value which is going to be equal to minus 0.302, and that's radians per second squared. So we found everything. We found the acceleration of the center of mass. We found the two components, and from here, of course, you can find what's the resultant, what's the absolute value of the acceleration, simply by doing this if you're interested. So you can just do Pythagoras and find the magnitude of the total acceleration. You can apply this, but we found each component, they're both positive, so that means the rocket is accelerating to the left as well as upwards, and the angular velocity is negative, meaning that there is an angular acceleration which is 0.302 radians per second squared clockwise. And that's the end of the question.